Hello, everyone. This is Tom Oxley. I'm sorry I can't be there in person, but I'm very excited to be presenting on our project assessing an endovascular brain-computer interface. Okay, so I am currently in New York City, where I'm running a company called Synchron, and I'm still on faculty of Mount Sinai Hospital, an interventional neurologist, as well as the Department of Medicine at the University of Melbourne, where the origin of this project really came from. So I do have a disclosure in that I'm the founding CEO and stockholder of Synchron, and the devices and procedures demonstrated in this presentation are still classified as investigational by the FDA. Okay, so I'm going to take you through the problem that we're trying to make an impact in with the use of a brain-computer interface, that of paralysis, what an endovascular BCI is, what the neurointerventional procedure looks like, the first-in-human results that are currently under review at a journal, and what the next stage of the clinical study is. Paralysis is a big problem. We work at the early stage of the treatment of paralysis in the treatment of stroke, but once there's been damage to the nervous system, there's typically not been any treatment or therapy for damaged nerves or neurons. And this is a really big problem. It's a big problem due to stroke, due to demyelination conditions like MS and NMO and transverse myelitis and ADEM and CIDP, neurodegeneration diseases like MND and muscular dystrophy, spinal cord injury due to trauma, traumatic brain injury, and even neuromuscular conditions. So there's a whole range of conditions that cause paralysis in our patients. And it's a very big problem. There are 5 million people in the US who have a severe paralysis syndrome. But when you start to consider the application of brain-computer interface, it actually is a larger problem even than that, because the concept of the BCI is that any condition that impairs your body's ability to engage with a computer, and the way that we typically engage with a computer is using our 10 fingers to control a mouse or a keyboard. And so any condition that impairs your ability to control a digital device is therefore treatable with a brain-computer interface. We happen to be starting in the very early stages of our clinical journey in the patient population that can be well defined, that is paralysis. So if you think about how we utilize digital devices to control our lives or to function within our lives, it starts with the intention of control within the motor cortex. And we don't think about this very much, but we know what the motor cortex does, but motor intention derives from the motor cortex. Then the motor neurons carry that intention down from the cortex through the subcortex, the spinal cord, into the periphery, eventually to affect an actuator, or an effector, such as a muscle, to then engage with a digital device to, for example, send your text message to your wife. So the concept with the BCI is that you go straight to the source of the motor intent. You bypass the entire journey of that signal of the message of the motor actuator all the way through to the digital device and create a bypass directly from brain to digital device, thereby offering a solution for any of the number of conditions that exist along that anatomical journey. So BCI is a broad concept for the engagement between an area of brain, and really we mean cortex, to interact with an external device that restores some lost brain function. And the types of brain function that most groups who are working in BCI right now are focused on is in the motor system, but there are other applications as well. And there are examples of all other ranges, but the concept is that you can really think of a BCI like a neuroprosthesis. BCI is synonymous with neuroprosthesis in my mind, in that a neuroprosthesis engages directly with the cortex or central nervous system and restores a lost bodily function, brain function. I think the early work, I'm not going to talk about the work around the Utah array, which was really the cornerstone of brain-computer interface work over the last 20 years. First reported by Lee Hochberg et al. In Nature 2006, in a very exciting piece that I first read in 2008, which utilized the Utah array to control an external robotic limb in a patient with severe stroke. Fast forward to 2016, and this was the first paper that came out in New England Journal, which was demonstration of not a penetrating array that goes directly into the brain, but rather a, let's just get that a bit small, move over here. But rather use a surface array to record ECOG, in this case, a subdural array, implanted via craniotomy, but utilizing ECOG to control an external device. This was a really big deal because there have been challenges in translating applications of the Utah array all the way through to FDA approval. And there are very famous examples of groups and companies that are working on that problem right now, invasive needles. There are problems that come with putting needles directly into the brain. If you go onto the surface of the brain, you have a trade-off in the amount of information you can record from the brain, but you have a much more stable system that utilizes signal that can last for a long time for reasons that I'll get into. So this was a big deal. This was a Dutch group led by Nick Ramsey. Van Stiesel was the primary author. This is Nick Ramsey's group. Open craniotomy, a 16-channel array, 2 bipolar features, and they utilized low frequency changes that occurred when the patient attempted to open and close her fist. It was a single output, high accuracy. It was very slow, but it was very robust. And for this patient who was ventilator dependent, locked in syndrome due to ALS, this became her primary form of communication. And it continued to work for years, and it superseded the use of eye tracking because it was not light dependent, didn't require calibration every day, and it just worked. So it was a sign for me that BCI, had a future if you could do a few things, including making it fully implantable, making it safe over a long period of time. But for my mind, the question was, is there a way that we can do this that does not require craniotomy? Fast forward to last year, and I'm not going to spend too much time on this, but for my mind, Eddie Chang right now is probably the preeminent BCI researcher utilizing ECOG at UCSF. A phenomenal, brilliant, and humble person who is not only discovering elements of how the motor system works, but building these incredible machine learning models that can, in this case, utilize word prediction and apply data into an application that enables patients to communicate and attempt to speak. For me, at a high level, this demonstrated that if you can record surface recordings from the top of the brain, you don't need to go with penetrating needle electrodes. You can derive huge amounts of information and data, build models, and create outcomes that demonstrate that BCI has a really bright future, in that the ability to take the data and improve and improve and improve, utilize machine learning. There's going to be this, generational improvement that comes with continued learnings. This is what the Utah array looks like as distinct from a surface electrode, penetrating electrode array. Currently under investigation, comes with challenges, really high data rates, massive data outputs, but the real challenges around biocompatibility due to the impedance changes that happen with gliosis over periods of time. But the linchpin of research over a number of years. So the concept that I had 10 years ago was, can we do all this from an endovascular system? Can we build sensors onto the inside of a blood vessel that can live within the body for a lifetime? We know that can happen based upon all the other work we do with stents and coils and other devices that live. But can we bring electronics into neurointervention, essentially? And so the first patent that I wrote in a Starbucks was putting a Utah array onto a stent. We didn't ever end up building that, but 10 years down the line, this is what the Stentrode looks like. It's a self-expanding stent that utilizes all of the properties of nitinol that we know so well, and then builds a second layer of metal. One of the major things that we had to figure out was, how do you manufacture a stent where there are 2 layers of metal? And that required a complete overhaul of manufacturing stents. So here's the concept of the device that's currently under investigation, not the immediate version right now, but stent inside the superior sagittal sinus, splits the left and right cortices in the motor cortex, records surface potentials from what is parasagittal regions, so lower limb representation of homunculus. Device comes down through the venous system out of the jugular vein into a device that sits in the chest. To put all that into, and then we record and we use different types of motor recordings that are representative of attempted types of movements. And they're spatially represented, they're distinguishable, they're classifiable, and then we convert those into individual discrete outputs that form the basis of switches or clicks that can drive systems over Bluetooth. So putting that all together, device inside a blood vessel, electrodes on a stent, self-expanded, connected to a lead, running out of the venous network, out of the brain, without any craniotomy requirement. Okay, so we're 10 minutes in. So I'm going to spend about 10 minutes talking through the neurointerventional procedure that we have developed, primarily with Peter Mitchell as the primary principal investigator based in Melbourne, Australia, who has conducted the first 4 procedures in Australia. Talk about pre-implant planning, co-registration, accessing the sinus, deploying, and then the transmission unit. So we are in the venous system. We're utilizing the superior sagittal sinus. So the trajectory is up through the jugular vein, transverse sinus, superior sagittal sinus. Patients have MRIs, both structural MR venogram and then functional MRI, to identify where the motor cortex is, where the precentral gyrus is, M1, in relation to the venous network. And then we take that information from the MR into the angio suite, do a spin in the angio suite when the patients first come in, make sure their heads don't move, had them under a GA, and then access the venous network. We are doing arterial access as well for angiography, but that's primarily to get the venous phase, because the mapping of the cortical veins is very important, because you really have to know where you are. And you do the co-registration, and if that works, great, beautiful. But the identification of local cortical venous anatomy and then a lot of studying of that before you do the procedure is very important to make sure that you are absolutely in the right spot. So we're entering into a phase of functional localization during neurointervention. So we get into the, so basically access using a microwire, microcatheter into the superior sagittal sinus, then delivering a 6 French sheath into these target locations, preparing for the delivery of the Stentrode. And then this is, the Stentrode is prepared or loaded inside a 4 French catheter. So the Stentrode comes preloaded in a 4 French catheter. You bring that up in the 6 French, and then you pull back the 6 French with your eyes on the markers and unsheath the device, and it feels a lot like a Stentrode delivery. We've got a radial force that's around Stentrode, basically. Once it's in place, you then do a run to make sure that the vessels are open. You can see the device. I'm sitting in there, and here is a spin of so you can see the lead coming out through the transverse sinus, presagittal sinus. You can't see the device very well, but it's open up there. But then this is a reconstructed dyna demonstrating the opened up device inside the target location. Okay, so then you've got your lead coming out of the jugular vein, and you then have to create a pocket, do a tunnel from the access point in the jugular vein, just above the just in the sternocleidomastoid insertion, a small tunneling down to the infraclavicular region, and we put in what we're calling the implanted receiver transmitter unit, and then we do a check of the data flowing in the angiography suite to make sure we have ECOG running. And that's what the IRTU looks like here on the X-ray post-implant. So, the same location for a cardiac pacemaker with a lead going up into the brain through the venous network. Patients are on dual antiplatelet therapy for 3 months and then single agent aspirin for at least 12 months. That was based upon, what we do for transverse sinus stenting for IIH. Okay. So we've conducted a first-in-human study. That study is closed. It's currently under review with a journal. We have published some very early results. They were published in JNIS, just the first very early results. But we now have longer-term safety data, and we've moved on to a second stage of the clinical study, which I'll present in a minute. And so here's a reconstruction of many things. The pre-MR structure with the fMRI labeling of activation, with the MRV reconstruction, with the post-CT, they can't have an MR after the device is in, with the post-CT for electrode localization, showing where we've been able to land. And there has been a tendency for the device to slip back just a few millimeters back to over sensory cortex. So, there are lots of learnings happening over the delivery of the system, getting it right over the primary motor cortex, but we're getting deliveries within an error of 5 millimeters and getting better and better every time. The FDA wanted us to look at primary outcomes that are device-related SAEs, resulting in deaths or permanent disability. In other words, stroke. We've not had any of those events. And then secondary safety endpoints FDA were very interested in were device migration, thrombosis, and vessel occlusion. So to look at that, we did CT venography at 3 months and 12 months. There's been zero migration and there's been zero vessel occlusion. There's been zero thrombus formation with very high quality CT venograms, all patients taking their antiplatelet agents. There have been no thrombotic events. There have been some non-serious events. Headache has happened in about half of the patients for a couple of weeks, simple analgesia. Similar headache to what is happening with transverse sinus stenting. It's probably due to some dural irritation, which resolves after a couple of weeks. And there's bruising at the neck site. We're holding pressure to close the venous access and the jugular vein. The patients are on aspirin and clopidogrel, and we use heparin for the procedure. So triple therapy, not surprising to be having some bruising, post-op bruising around the neck. Here's an example of one of our patients with the device. There's the sagittal view of baseline and then 3 months and 12 months showing there's no movement of the device. This is just to make the point. This is a paper that, this is actually from an animal work. This is not human data, but I just wanted to show, this is the data we presented to the FDA to mount the argument for why we do 90 days of dual antiplatelet therapy. The image here, so this is an animal model with the device implanted at baseline, and then here the device after 45 days. And what we demonstrated in this preclinical study was that 95% of the device becomes endothelialized within 45 days, possibly sooner. We didn't have time points between the two, so there's still some uncertainty around how quickly the endothelialization happens. But this is the justification for so we've gone conservative. Once the device is covered, the risk of thrombosis is reduced substantially. And so this was evidence that 90 days should be sufficient and possibly, quite conservative. It might be that 6 weeks is going to be enough, but we're right now running with 90 days. So then the way the system works and what we're doing in the study was we have the patients attempt to make movements of certain parts of their body. And we're in the parasagittal region, so lower limb representation. So we usually start with different types of ankle movements or lower limb movements that generates change in NECOG signal that we can threshold, extract, classify, and turn into a clear output. So, in the end, it becomes basically like a transistor, a 1 or a 0 for a certain type of movement in the body. And we then turn that into a click or a switch, and we send that switch or click over Bluetooth and have the patient control anything over Bluetooth. And we're building out clinical studies now to figure out the best way to utilize that type of control for systems that have a clinically meaningful outcome for the patients who are paralyzed. Importantly, Signal stability was something that we've looked at very closely. And we have demonstrated out to 12 months in our first 4 patients that signal stability is statistically stable. And, over time, there are certain, correct character minute varies from around 10 up to 30 in terms of typing speed. Selection accuracy, we have set thresholding. It has to be accurate, otherwise it's not useful. So we've set high accuracies and, work towards that. And, working out towards multiple switch decoding. And the question for BCI, from the way that we're going about this, is how many of these switches can you start to get out? And so, our data science challenge is to build software systems that enable the patient to get better and better at using these systems. But for a minimal viable product, for a minimal viable outcome, what can we have patients with just a low number of switches do? And so using things like your iPhone or Microsoft tablets with a low number of switches is very meaningful. So we use gamification to help the patients get better and better at the utilization of these switches. And then we apply these into use cases, sometimes in multimodal applications, but we're moving away from eye tracking now. But initially we started with the combination of eye tracking to get the cursor around the screen, and then the use of different switches to say left click, right click, zoom click. And probably the most powerful application immediately, this was our patient number 1 in Australia with a very sophisticated setup of books to hold up his tablet with a complicated system, was to use WhatsApp. And so, the navigation of using clicks around like the keyboard, think about, getting around a keyboard to change your Netflix password using your smart TV controller. That's kind of the target that we have for the first application. So once you're onto the keyboard in this space, you open up WhatsApp, you can type, you suddenly are able to text message. And for this patient who had ALS or MND, who had lost the ability to text message, this was a hugely meaningful moment in his life where he was going in one direction due to the ALS of a reducing of his ability to live independently in the world, to suddenly getting back control over his digital ecosystem. So that's what BCI is really about, from my mind, is re-enabling your access into the digital ecosystem that we all take for granted now, but which you lose if you have conditions that stop your ability to type. So here's another one of our patients. He's also navigating his way through the keyboard, and he's sending a text message to his wife, who is in another room, who typically would have to be coming and regularly checking on him to see if anything was needed. And is this running? Yes, it's a bit slow. And then she is doing what she needs to do. Maybe she's out of the house, maybe she's somewhere else, but they are now in communication digitally, which was not possible beforehand. Smart system at home. So I think you get the idea here, like these Bluetooth control systems can use any sorts of things. So starting to wrap up now, what's next is we have approval from the FDA to continue. We have our first patient enrolled in New York. Pittsburgh has just opened as a site, UPMC, with Raul Magira. Sharam Majidi was an interventionist who performed the first patient in New York. We have a total of 6 patients to be enrolled in our early feasibility study, and another 10 in the Switch 2 study in Australia, which are very similar studies. Again, we're looking at safety outcomes, but we're starting to get, and I don't have all of the pre-specified outcomes here, but we've worked very hard to, I think the real challenge for BCI is what are the outcomes, what does efficacy really look like? And what does efficacy look like in a way that Medicare is going to pay for these devices for our patients? And so, the diary is one of them, but I haven't listed them all here because it's still a work in progress. But I would consider this COMMAND study as a efficacy finding study as we begin to explore the use of the BCI to control digital systems that improve functional independence in a way that moves the needle on health outcomes. So the patient has to be between 21 and 75, severe paralysis in both arms and legs, English speaking, local to Pittsburgh and New York, accessibility to a caregiver, unable to perform finger tapping tests to a certain degree. In regard to certain conditions, for spinal cord injury, we're looking for high cervical, ventilator dependent is fine. For basilar stroke, so we need preserved cortical activity. Speech is not an inclusion or exclusion criteria. It's more about whether your hands are working or not. Multiple sclerosis needs to be fully progressed, resulting in severe paralysis, and muscular dystrophy or other conditions that we're looking to enroll in. So just to leave you, this was the moment our first patient was able to actually write out a sentence. Now he went on to then, use this on WhatsApp. So at this point, his wife still didn't fully get what had happened here, but this was the moment he wrote the first sentence. And just the joy on the two of their faces after this gentleman having progressed through his life with ALS and losing his ability, it was just a moment where the world opened back up for them. And I think that's the power of BCI. That's why I'm so excited about where BCI is going. And this is a completely new world for neurointervention. And, for my mind, neurointervention is the solution for BCI. The problem with BCI has been the safety, long-term safety and commercial translation that comes with craniotomy and all the challenges. And there will be other versions, but neurointervention has now moved to the forefront as the solution for BCI. And I think it's going to be a very exciting time as this technology rolls out over the next 3 to 5 years and offers new hope for our patients. So thank you very much. And I hope to, be available if there are any questions, or if we're gearing up towards the pivotal study over the next couple of years. You can reach out to me via email. My email is toxley@synchron.com. We'd love to hear from you. Thank you very much.
Thank you so much, Tom. Are you here with us? Could you hear us?
Hi.
Thank you so much for joining. Again, fantastic work. I mean, it's so obviously life-changing. And any question here in the audience?
Hey, thanks for this enlightening lecture. This could be a basic question, but I'm curious, why did you guys decide to go with a superior sagittal sinus versus, for example, an arterial vessel? You're away from the motor cortex. So I'm curious about the location. And if there's a subdural down the line or atrophy, would that probably make the cortex further away from that stent? So do you have to have a new stent there? Like, is one stent enough to cover the whole brain? Just honest your thoughts.
Yeah, I mean, the arterial system is compelling. I mean, the activity that we want to record in the cortex is in, the neocortex. So arterial vessels in the neocortex near the M1 region of motor cortex, that's very hard to get to. I mean, you're talking about distal MCA branches, and there's not much margin for error with any clot formation in any MCA branch, really. There are some external carotid branches, but they're not always near the M1 region. So the venous, network is what gives access to superficial neocortex. And yes, more coverage is better than less. There are huge technical challenges in delivering large channel counts into blood vessels that can exist safely. So there's a trade-off in how much coverage you can get in a first-generation system, with constraints around the hardware system that we've had to build. So it was a, compromise across all things, hardware, software, and neuroscience and an algorithm that had to be made to get the right balance for the first-generation system. But we know we're just at the beginning.
Thank you.
Do you require any antiplatelets chronically for these, or what are the recommendations?
Yeah, we basically looked at the literature on transverse sinus stenting for pseudotumor cerebri, or IIH. So it's dual antiplatelets, aspirin and clopidogrel for 3 months, and then single agent aspirin for 12 months.
Tom, this is Tudor Jovin. You probably would. It's
Hi, Tudor.
Expected to see me here or hear from me here, but I'm also visiting. So I'm always fascinated by your lecture and what you're doing. It's incredibly cutting edge, and I think of great potential. Can you tell us where do you see this technology be applied in 10 years? What will Nima and Ricardo and Eric do here at Baptist in 10 years when everything is FDA approved? What kind of applications are we talking about?
10 years is not that long away for a class 3 medical device. So I think on a 5-year horizon, we have completed a pivotal study and we're looking at FDA approval. On a 10-year horizon, we're looking at getting this technology out to centers. So I think, I think what's more interesting is a 20-year horizon where this technology becomes, I think the possibility that this technology outpaces volume of stroke is substantial, given the size of the problem and the availability of elective cases for our neurointerventional community. I think this is going to become a very large elective component of our practice over a 15 to 20-year horizon. I think BCI commences in the domain of motor cortex for the treatment of paralysis, but I think there are going to be huge breakthroughs coming in areas that traditionally have required craniotomy. So deep brain stimulation therapies for movement disorders, responsive stimulation for epilepsy, sensing for epilepsy. I think, I have a view around a range of areas, depression, that are going to open up in the same way that in cardiology, cardiothoracics, developed solutions that could be delivered from an endovascular point of view. I think the same thing might happen where our patients can avoid craniotomy and we figure out ways to either sense or stimulate regions of brain from blood vessels.
Right. So you think that functional neurosurgery is going endovascular and the time frame for that is 20 years, not 10?
I think,
sorry,
well, I don't know what others are going to do. I think what we're going to do is, it's really hard to build a technology platform that has the mechanical component of endovascular, the electronics and communication protocols of telemetry, the analytics AI components of data analysis, the software components of app control. I think all of these things had to come together. And so I think we are going to be really focused on this first application. But once we have this platform approved, then I have a vision of spreading out to a range of different applications. But I think, yeah, it's going to be on a 10-year horizon before we start to move into the other domains. But we have a patent portfolio that are going to open up these different areas. But we've got to be focused we've got to learn to walk before we can run. But I do think that neurointerventional electrophysiology is going to be a very large discipline. I think it's going to grow a lot.
Thank you so much.